Hi guys, my name is Behruz. Welcome back to the Rust blockchain tutorial series. Today we are going to building a marker tree for this blockchain application. And we'll mainly just be finishing off the transaction system so that we can move on to adding a network system to our blockchain. Now let's talk about marker trees. Marker trees are essentially another optimization mechanism, much like the UTXO set. I mentioned in the last tutorial that the full Bitcoin database take up about 4 or 5 or 600 gigabytes of disk space. And now, because Bitcoin itself is decentralized, every node inside of the network must have its own independent and self-sufficient node which will store a copy of the blockchain as Bitcoin grew more and more. People had to get full node on the machine, and it's become less likely that people would really want to install such a large program just to access Bitcoin. Also, full-fledged nodes have certain responsibilities on the network. For instance, full-fledged nodes need to verify, transact, and blocks, and not every user who uses a blockchain wants to do these things. In the original Bitcoin white paper, the main solution for this problem was called a simplified payment verification system, or SPV. The SPV is essentially a write Bitcoin node that doesn't need to download the entire blockchain, and it doesn't verify block or transaction. And said it finds a transaction in blocks, and it's linked to a full node which will retrieve the necessary data for it. The idea is that you can run a ton of light wallet nodes on the top of just one full node. So maybe 100 people have to have the entire blockchain database on their machine, and then maybe 100,000 people have just a wallet application on their machine. They use this SPV system. For this SPV system to actually work, there needs to be a way to check if a block contains a transaction without actually downloading the block itself, and this is where the marker tree comes into play. Marker trees are used by Bitcoin to obtain transaction hashes, and they save the inside of a block hasher, and it's considered by the proof of work system up until now. We've just kind of concatenated the hashes for each of our transaction into a block and then applied a SHA-256 algorithm to them. This is perfectly fine, and it's a good way of getting a unique representation of the transaction inside of the block, but it doesn't have the benefit of a marker tree. Marker trees are an essential part of blockchain for data integrity. Each block in the blockchain can contain multiple transactions which each contain data. In this example, there are 4 transactions, TX1, 2, 3, and 4. Each of the 4 transaction data is passed through a hash function and generate full unique hashes, one for each transaction. Pair of hashes are then combined and passed through the hash function again. This process generates 2 separate and unique hash, which are each based on upon uh, combine of the 2 hashes relating to the 2 transactions. The 2 hashes are then combined and passed through a hash function again, and this result a single root hash, forming a complete marker tree. One of the main rules of the marker tree is that the leaves of the trees must always be even. So it's inside of the block, we only have 3 transactions. What will happen with the transaction 4 is that will actually be a copy of the transaction 3. So we can have a transaction 1, 2, 3, and then transaction 4 will be a transaction 3 copied, and then we'll do the same exact process to create our marker tree root. Okay, let's go to our code in the block.rs file and implement our marker tree to the block. The library we are going to use is marker marker CBT. So we added before at the first video. You can see and watch the first video how we can add all libraries we need for the to create this blockchain. Okay, for merge our transaction with each other and create a unique hash to get a single root hash, we need to create another struct. So the struct is a merge tx. Then we use a trade from the CBT library to combine of each right and left transaction to each other and use the SHA-256 to generate unique hash. As you can see, we create a new of SHA-260 and we are going to clone the left U8 or transactions data or byte. Then we are going to append the right to the data. Then we pass to the input method from the hasher. At the end, we get the result and return the unique hash. So inside of the block, we create another method to hash the transaction with this marker tree. So we create hash transactions and the result is going to return a VQ8. So inside of this method, we create a new merge transactions. Then we walk through to entire transaction one by one and push to this transaction, and then we use a merge tx from the with the library cbmt, and we build a marker tree and pass a transaction here. Then at the end we return a tree.root for VQ8. As you can see, we generate this here. Then we use a hash transaction inside of the preproof hash data instead of the pass clone of the transaction here. Okay, let's go test our blockchain again because it's not going to affect our functionality to entire blockchain. So our marker tree functionality is done. I want to delete the data because I want to create a new blockchain. So let's do that. Okay, first we create a wallet, then we create a blockchain with this address. Then we are going to get balance of this specific address to see everything is fine and work. Get balance, and you can see 100 tokens here exist in this address. Okay, I hope you enjoyed this video. In the next video, I'm going to talk about a network layer and to finish our simple blockchain with a network. See you in the next video.